In this video, we're going to talk about hypothesis tests specifically for a population proportion. So first we're going to explain the logic of hypothesis testing and then go about actually doing those hypothesis tests. So in this first example, we have a researcher who obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. Does this suggest that more than 50% of the people favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is some proportion 50% or less, and we just happened to survey a majority in favor of the policy? So we're supposed to use an appropriate hypothesis test with a significance level of alpha equals 0.05. So in the blue letters we can see here are all the things that we have to do when hypothesis testing. So first, we're going to define H0 and H1. Then we're going to list out some requirements and assumptions. And then we're going to find the test statistic and the p-value. And then at the end, we'll make a decision and a conclusion. So if you're taking notes, you should be writing down this list, because this list is what we're going to be using for the rest of this unit. We're going to do this list over and over and over and over again. Okay, so let's start with determining the null and alternative hypotheses. The hypotheses can be structured in one of three ways. So anytime that we start a hypothesis test, we have to decide which one of these we're going to use. Now, notice on here, they're using P a lot, and that's because we're talking about a population proportion in this example. We're talking about people who are in favor of banning cell phone use or not. And so because this is qualitative data, people would be saying yes or no, then we're using a proportion. So that's why it's using P's down here. So first we have our two-tailed test. And for the two-tailed test, H0 would be that P is equal to P0. All right, so that's just that the population proportion is equal to the proportion that was given to us. P0 is like original proportion, right? H1 says P is not equal to P0. So that would make it two-tailed, because if it's not equal, it could be either to the left or to the right. Left-tailed, H0, again, is P equals P0, but then H1 is that P would be less than P0, and for right-tailed, H0 is that P equals P0, again, but H1 is P is greater than P0. So notice across all of those different tests, H0 is always the same. P is equal to whatever the assumed value of the population proportion is. And then H1 is where it actually changes. But we're still using P, we're still using P0. It's just a matter of whether it's not equal to, less than, or greater than. So for example here, it asked if this suggests that more than 50% of the people were in favor of the policy. So because I'm looking for more than, that means we want to use a right-tailed test. And then we're not going to usually say P equals P0 explicitly. What we want to do is actually put in a value for P0, and that value would be that whatever the assumed value of the population proportion was. And in this case, the assumed value was 50%. So the hypotheses would be as follows for this example. H0 is that P is equal to 0.5, and H1 is that P is greater than 0.5. Then we have to check for some assumptions before we're allowed to do our hypothesis testing. One of the assumptions that we have to check is that the sample is obtained by simple random sampling. Number two, we check that n times P0 times 1 minus P0 is greater than or equal to 10. This is establishing our normality. This is something that we've already talked about whenever we were doing confidence intervals. And then the third thing we would check for is that the sample values are independent of each other, or that n is less than 0.05 times capital N. So let's check this for our problem. First of all, they said it was a random sample, so we can check off that one. And then when we plug in our values for the second condition, 1,000 times 0.5 times 1 minus 0.5, we get 250, which is greater than 10. So we're good there. And then on the last one, it says that this is a sample of 1,000 people. And we can assume that this is 5% of the population. Now, we've seen this one before, and I just want to take a minute to say why we usually just say yes on that one, even though we don't technically know capital N or the population size. Think about, in this case, we're talking about just like people who own cell phones. So we're talking millions of people here. And if you were to take 5% of 1 million, or do 0.05 times 1 million, you would get, let me see here, 50,000, okay? So unless my sample is more than 50,000 people, I don't really have to worry about this condition. It's something that we always check just to make sure, but typically when we do our problems, that one is like an automatic. Okay. Also, we want to recall how we described our sampling distribution of p hat. We said that p hat would be, the sampling distribution of p hat would be approximately normal if, number one, well, I was thinking means. For this one, we check that n times p times 1 minus p is greater than 10, which we just did. And then we established that mu sub p hat is always equal to p, and the standard deviation sigma sub p hat is equal to the square root of p times 1 minus p over n. So applying it to our problem, we had n was 1,000, p is 0.5, and so mu sub p hat is equal to 0.5. And then sigma sub p hat, when we plug in all those numbers, we get approximately 0.016. And then we have a picture here, an image of a normal curve where we can see the mean right in the middle is 0.5, and then we're using that standard error to go 1 standard deviation to the right and 1 standard deviation to the left. So that's a visual of our sampling distribution of our sample proportion, p hat. The next part of the process is to compute the test statistic and the p-value, and we're going to do that using StatCrunch. So first step is, if necessary, we would enter our raw data into column 1. Usually that's already given to us. If it's not given to us, that means we might have a summary. So we're going to select stat, proportion stats, and then 1 sample. If we have raw data, we would choose with data. And if we have summarized data, then we would choose with summary. And then I'm going to walk you through the rest of that. We do have to choose hypothesis test radio button before we did confidence intervals. So we're going to the same place that we went for that. But now we're going to choose hypothesis testing and then enter in what our null and alternative hypotheses were. Okay, let's go do this one together. I have all of it here, but I'm actually going to go back on my slides to where we had. Okay, and I have pulled up a blank StatCrunch spreadsheet here. And so we are going to stat, proportion stats, 1 sample. In this problem with the cell phones, they did not give us raw data. I don't see anything in my spreadsheet. So we're going to go to with summary. And you'll know really quick if you really have a summary or not, because then you'd be looking at this going, well, what are the number of successes and number of observations, right? So in this problem, our successes is people said that they were in favor of banning cell phone use while driving. So that will put our 534 there, and our number of observations is how many people were in that sample, which is 1,000. Then we make sure that this radio button is selected next to hypothesis test. Then we can see H naught is already set to P equals, and then we may need to change this number. So let's go check. What was our population proportion? 50%, 0.5. So this actually is already correct in there. And then H sub A is our alternative hypothesis. Note how they use an A instead of a 1. When we write it down, we do 1. But in StatCrunch, they use an A. And it says P, and then it has a drop down here of, for me to pick not equal to, less than, or greater than. For our problem, we wanted more than, yeah. So we want, it says, does this suggest that more than 50% of the people favor the policy? So we want greater than, and then we can hit compute. All right. And then we get a summary here. So it gives us our proportion P. It tells us the count and the total, 534, 1,000. It tells us our sample proportion, which is 0.534. Our standard error here is 0.016 if we round up, which is what we already calculated by hand. And then it gives us something called a z-statistic, 2.1503488, and a p-value, 0.0158. All right, so let's go look to see how we're going to use this information. Okay, so on this screen, we're circling where the z-stat and the p-value were, just to point that out. So what the p-value is telling us is the probability of obtaining the sample proportion p hat, or more extreme if h naught is actually true. Okay, so in our example, we got a p-value of 0.0158. So if we had 100 people, we could multiply that by 100, it rounds up to 2. So that would mean that about 2 samples in 100 will give a sample proportion as high or higher than the one we obtained if the population proportion really is 0.5. Okay, this can be a little bit confusing to figure out, but ultimately what they're saying is, okay, we assumed that the population proportion was 50% or 0.5, right? We're assuming that, but that's the population. Then we did a study, we collected some data and got a sample. And from that sample, it turned out that we actually got like 53.4%, something like that. So if the population proportion really is 50%, is it weird that I did my own study and got something slightly higher than that? Okay, so that's what we're ultimately saying here is when we get this p-value, it's like, what's the probability that that would happen for me if the population proportion really is 50%? Okay. And so that's what we're testing here. We get a probability that's pretty low. So it's saying like, you know, really, if we did like 100 samples just like yours, there's only 2 of them that would get the same results as you. So that's pretty low. And so because those results are unusual, we take this as evidence against the statement and the null hypothesis. So we're kind of questioning if the population proportion really is 0.5 like we claimed. So here's a visual of those 3 different tests. Our left-tailed test is looking at the area to the left of Z naught, which is our Z-score or our Z-statistic that we just got. So, and remember the area under the curve is just a probability, okay? For the two-tailed test, we're looking in either direction of that Z-statistic. And then for a right-tailed test, we're only looking to the area of the right, okay? Let's look a little bit more about that test statistic, Z naught. This tells us how many standard deviations our sample proportion is from the mean P naught. Okay, so we have P naught right in the middle, that's our mean. And then our sample statistic, P hat, is usually a little bit to the left or to the right of that. Z stat is telling us, or Z naught, our test statistic is telling us how many standard deviations away our sample proportion was, okay? And we can see the calculation for that here. Remember, to calculate a z-score, we take the data value, subtract the mean, and divide that by the standard deviation. So our data value is p hat, our mean is p naught, and then on the bottom we have that calculation for standard deviation. Square root of p naught times 1 minus p naught, all divided by n. In this example, z equals 2.15. We don't actually have to calculate this by hand. We just did that in StatCrunch and it gave us this value. So recall, for our empirical rule, it told us that 95% of our data is within 2 standard deviations. So we know that this sample is out in the far tail of the distribution, right? That's why we say, oh, we want our probability. If it's less than 0.05, then that's weird because it'd be further than 2 standard deviations away from the mean, which is pretty far away. All right, for step 4, this is where we actually make a decision. So if our p-value is less than alpha, and at the beginning we said our alpha was 0.05 or 5%, If the p-value is less than that, we would reject the null hypothesis. We're saying it doesn't really make sense to get these results if our null hypothesis is what we said it was. If the p-value is greater than alpha, we would fail to reject the null hypothesis. So in this case, we would be saying our probability is actually pretty high that this would occur. So we don't have anything to worry about. There's nothing to question here. And so if we fail to reject the null hypothesis, that means we'll just keep assuming that it's true. So if the probability of getting a sample statistic as extreme or more extreme than the one obtained is small, under the assumption the statement in the null hypothesis is true, we reject the null hypothesis. So in our example, we're going to reject H0 because our P was 0.0158, which was less than 0.05. So in step 5, even though we just made that decision, that was more like statistics talk. P is less than alpha, and so we reject H0. Okay, but now we want to put this into words that people can actually understand. Okay, so we're going to put this back in context. What we would say is that there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that more than 50% of the voters favor the policy banning cell phone use while driving. Okay, so since we rejected H0, which was that it was equal to 0.5, that means we're going with the alternative that was more than 0.5 or more than 50%. Okay. Note the structure of that sentence. The structure of our sentence, conclusion and context will always be the same. Okay, so we'll say there is or is not sufficient evidence at the, and then you state the significance level to conclude that, and then you give your conclusion. So usually it's like you're stating either the null hypothesis or the alternative, whichever one we went with, but you're putting it back in plain English for what the problem was representing. Okay, so an informal way to say this is that our data suggests that more than 50% of the population supports banning cell phone use while driving. Okay, when our observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant. When results are found to be statistically significant, we reject the null hypothesis. Whew, okay, that was a really long video. I'm sorry, but that whole process kind of goes all together so that everything we just did is how every hypothesis testing problem works. So from now on, hopefully it'll be a little faster now that we know all the steps. In the next video, we're going to do some examples of hypothesis testing.